Good morning and welcome to another episode of This is Automation Live. I'm your host, Corey Dallas, and we are very happy to have you with us today. We will be wrapping up our three-part series on motors today. So if you haven't checked out the other two episodes, the first one was motor technologies, and the next one after that was about the speed torque curve. And today we will be talking about motor sizing. So if you've ever come across a motor application, you didn't even know where to start when selecting a motor, this will be a great introduction for you. We'll be talking about a few different methods that you can use. So next time that you approach a motor sizing application, you'll know exactly what to do. Coming up next, we have an episode about real-time industrial Ethernet, focusing on Ethernet PowerLink, which is one of the many industrial Ethernet standards out there, but we'll be talking about some of the interesting mechanisms that are behind PowerLink and how it may be useful in your application and what to look for when looking at different industrial Ethernet options. So let's go ahead and kick off our discussion about motor sizing. There's two kind of main approaches that we'll be talking about today. One is the manual approach, kind of the old school approach, if you will. And then we'll also be talking about some software-based approaches that you can use. Both of them are perfectly viable, and we'll talk about some of the pros and cons to each of them. But before we get into the details of motor sizing, I wanted to introduce everybody to some basic terminology so that we're all on the same page. If you watch the episode on the speed torque curve, this will be a familiar screen. So when we're looking at speed and torque, they're pretty simple concepts, but wanted to just give a quick introduction to them. So when we say speed, we're really talking about rotational speed. This is just the number of revolutions over time. This is typically measured or given in units of rotations per minute, RPM, or sometimes, but less common in industrial applications, in radians per second. When we look at torque, torque is just rotational force. So if you think about the concept of linear force, is a pretty common one that we all are familiar with. You know, you put a force on something. Torque is basically the rotational version of that. So this is, the easiest way you can think about that is, force being applied at some radius r in the image that we see there. This is typically in units of Newton meters or inch pounds. One new term we're going to introduce today is called moment of inertia. So we'll be talking about specifically the mass moment of inertia. This easiest way to think of this is the resistance to rotation. So any sort of object's resistance to rotation. So the more resistant it is to rotation, the higher moment of inertia it's going to have, and the less resistant, the lower moment of inertia. The units for this one are kind of interesting. So it's typically going to be shown in kilograms centimeter squared, or sometimes kilogram meter squared, or ounce inches squared, or pound mass inches squared, depending on where you're looking and which part of the world you're in. So two examples we're looking at on the screen here. You can imagine these as long cylinders. So we're looking at them end on. The image on the left there is a solid cylinder with a radius of r, and the equation there just to the left is actually the equation for the moment of inertia for that object. So you can see it's 1/2 the mass of the object times that radius squared. Now, to kind of explain the concept of moment of inertia, we've got another object. Now let's assume it has the same mass. So it's got the same outer radius, but there's actually a hollow part in the middle. So instead of being a solid cylinder, this is a hollow cylinder. Now you can imagine, to get the same mass, we would either need to change the density or change some of the geometric dimensions of the object. So let's just assume that this is a hollow cylinder with the same mass, so it's maybe a little bit longer than the solid cylinder. So you can see that the equation for that geometric object would be 1/2 the mass times the outer radius squared plus the inner radius squared. So you're actually going to get a higher moment of inertia for that object than you would for the solid object. Okay, so again, if you can think about this in your head, imagine holding a solid cylinder, and then imagine holding a cylinder where the mass is more concentrated to the outside. You can imagine that if you were to spin them, you would feel a higher resistance to rotation from the hollow cylinder. And this is basically the concept of like a flywheel, right? So it rotates to keep the some rotational energy, and those flywheels typically will have, you know, a high mass moment of inertia to make sure that they're very resistant to rotation, so they'll keep spinning. Okay, so that's a concept that we'll be talking about. So we won't get too much into the weeds as far as calculating this or anything, but it is a concept you should be familiar with. So when we talk about motor sizing, it's often good to look at it in the context of some sort of procedure, some sort of step-by-step. So the first thing that you're going to want to do is understand the electrical characteristics of your system. What is the supply voltage that you have available? Is it single phase or three phase? This is really going to inform your motor selection quite a lot. So it's something that you want to understand up front. This is either going to be something that is already existing in place, or maybe it is even a design decision that you can make. So that's just one thing you kind of need to know up front. And then from there, you kind of enter into this iterative loop. So the first part of that loop is the mechanics of the system. So you really need to know what the mechanics are in order to size the motor. So for example, you know, the first thing you'll probably need to know is this, you know, a rotary axis or a linear axis? What kind of gearing are you using? What kind of transformations are there? So for example, a rack and pinion, or belts or pulleys, those kind of things can seriously impact the motor sizing. So that's kind of the first thing that you need to nail down. What does my system actually look like, and how are all the components coupled together? From there, you'll want to define all of the loads and speeds in your system. So, you know, this would be any, you know, linear loads that there are, or rotational, as well as the speeds that you want, usually at the endpoint, and then you kind of take that through all of the, you know, mechanical transformations to understand how fast does the motor need to be moving. So once you have those two things defined, you can get a good idea of what your max values are going to be for torque and speed for your motor, as well as what the RMS values are. And we talked about RMS values being important in our speed torque curve episode, because there's some thermal considerations in motors where you can't always run, you know, at the peak performance of the motor, because it won't be able to cool itself down. So you'll be able to get your RMS and max values at this point, and then from there you should have all the information you need to select your motor. And then once you get your motor, you'll know which drive system to use. Now typically there is some iteration in this, that's why I'm showing it as a loop. So you may get to kind of your first iteration and realize, wow, this is a massive motor, or I need some insane gear reduction or something like that. So maybe you can make some modifications to your mechanics, introduce some gearing, some other changes to maybe make the motor selection a little bit more reasonable. The important note here is there's many possible combinations of, you know, mechanics and motors and drives that could you know, functionally make something work, but it may not be the most efficient or optimized system. So that's why this is a iterative process. So I mentioned there's two basic ways to go about sizing your motor. Step one is basically a manual motor sizing. This can be somewhat complicated, but if this is all you have available to you, that's what you'll have to do. So the example we have here on the screen, we've got a motor, which is the cylinder on the far left, some sort of coupling to a gearbox, and then a coupling to a rack and pinion. And that rack and pinion is moving a load. So if we were looking at a manual motor sizing for this application, it becomes somewhat complicated, because this rack and pinion has quite a lot of characteristics that can affect the motor sizing. So for example, the backlash, the friction of the guide, the rigidity of the rack, the length, the mass, the angles of the gearing, the pinion dimension, so the radius, the inertia, the mass, the efficiency of the rack and pinion, the degree of incline, so on and so forth. And there are these complexities in kind of every mechanical component of the system. So if you're trying to do this by hand, it may not be terrible for a small system, and you could easily then, you know, find your torques and speeds and compare that to your speed torque curve and select a motor. But what we mentioned is this is an iterative process, right? So to do all of these hand calculations over and over again, even if you put them into Excel, for example, it can get pretty complicated, especially if you want to change your mechanisms at all, change any transformations. and even just being able to quickly get data on motors and gearboxes. So that manual process is certainly possible, but the good thing is there are software tools out there to help us. So one of the tools that I can recommend is a tool called ServoSoft. If you're a user of B&R, it has B&R motors and drives and gearboxes already integrated into their databases, so you can pull those directly in, which is really nice. We looked at before, a rack and pinion system. It's doing all these same calculations that we were just talking about, but in the background and in a very nice, configuration-based approach. So you're not going to be able to miss any steps because it's going to walk you through everything. So, for example, we talk about all those different metrics. It's going to have, some conservative values in there by default, and then you are just going to put in, the additional information that you have. When defining your loads, for example, instead of having to manually calculate your moments of inertia, you can just put in the dimensions, the material that you have, and from there, you've got a really simple way to kind of build out the mechanics of your system. Then on the motion side, inside of ServoSoft, there's something called sequences. And sequences, again, this is something that is a little harder to do by hand. So we can actually define either a conservative set of motion profiles or even the full motion profile of a specific axis to understand what the speeds and torques are going to be throughout those different motion profiles. So you can make this pretty much as complicated as you need to and add multiple different sequences. So this is an example of what that would look like. So you can see here, I've just done a pretty simple movement profile, 1/3 acceleration. And from this, I'll be able to understand what the system is going to behave like. And from there, I can select my motor. Okay, so quickly, we will jump over into ServoSoft and just take a quick look at this. There's a nice wizard inside of ServoSoft to kind of walk you through those steps. So we'll look at that, and then we'll talk about one more approach to motor sizing. So you can see here, I've got a somewhat completed project already, but I'm just going to open the easy size wizard again to kind of walk you through this. So you can see the first thing is mechanics. So we'll select again here, let's say maybe it's a rack and pinion. I can put in all of my different requirements. Again, load in my moment of inertia, put the details of my load, the mass, thrust, if there is one, any limits. And then what I would do from there, move on to the next step, which will be defining any transformations that there may be. So in this case, I've got a gearbox in my system. So you'll notice if I select the transformation box there, I actually get this nice database of B&R gearboxes. So instead of having to go and look all that data up online, I can actually just pull it directly from there. And you can see I've got all of the curves with it as well. Moving beyond that to the actual motor selection, it's very similar to what we just looked at on the gearbox. Basically, we're just trying to match the rated for the motor to the required of our system. And ServoSoft gives us some nice outputs here, percentage of capability that we're using. So again, when we select our motor, it's going to give us a full database, and we can sort this list based on what meets our requirements. It's going to show us the speed torque curve, our RMS point, where we sit on that curve, as well as how much of that motor we're using. So again, you can look at all of the different curves in here. Again, we see our RMS point, so we know we're under that thermal limiting curve, and this motor is going to be sufficient for a requirement. There's lots of other tools inside here, but we won't go into too much detail for now, but I think you can kind of see the basics of it. We'll define the mechanics of the system, any transformations between our load and our motor. Then we select a motor, and from there, I didn't want to show this today, but we can select our drive from there as well. You may need to look at things like brake resistors or something like that, depending on the system. And the other nice thing with a software-based approach instead of a manual one is any sort of complicated multi-axis system is going to be a lot easier here, especially when you're looking at shared DC bus, those kind of things. That's all handled in the background of a tool like ServoSoft. So if you have a more than very simple solution, I would definitely recommend looking at a software approach like this. So I mentioned there's one more kind of approach that we'll be talking about today. And we've looked at what a manual approach could look like, what a software-based approach could look like, and there's one more that's kind of a subset of the software-based approach, and that is a simulation-based approach. So there are simulation tools out there that you may already be using for your system to understand the mechanics of the system and understand how all of the different components interplay. Or maybe you just have a system that's maybe a little complicated to model inside of a tool like ServoSoft, where we just have basic transformations. So that's where we can bring in a kind of model-based simulation tool and then integrate that with our servo sizing tool. So one of those is MapleSoft's MapleSim tool. And today we have a special guest with us, Blake from MapleSoft. Welcome, Blake.
Hi, Corey. Thanks for having me.
Thanks for being here. So Blake works with MapleSoft and has a background in physics and math and mechanical engineering, and is going to share with us today a little bit how we can use a simulation-based approach to better our servo sizing applications. All right, so Blake, I think you have some stuff to show us on the screen, so I'll go ahead and kick it over to you.
Awesome, thanks, Corey. So what we have here is bringing in a CAD. So we've developed this or created this in SolidWorks. We have a method just for interacting, click the different parts, kind of seeing how it looks. And then we have these circular things that we can see here. These are allowing me to define where I'm going to have motion, so rotation, translation. Once I've added them all, I would click accept and return, but I've already done this. Once I do this, I have all these CAD pieces that are appearing in MapleSim, and now I can connect them using multi-body joints. So for example, I can grab some revolute, and I can define rotation motion. I can grab prismatics, define translational motion. I connect everything together. And then really what I'm focusing on here is going to be the motor. So this is where my motor is actually kind of living. I can define some ramp profile, give it a probe, which then allows me to get quantities. So the torque is what I'm interested in. I run a simulation. And what's going to happen in this simulation is because I brought in a CAD, I'm going to get all those mass and inertia that we were talking about earlier, automatically calculated, automatically kind of connected together. So when I get this simulation, I'm getting something that's very accurate, and it's not lacking any of those dynamic effects. So on the left, we can see this 3D playback. I've got some boxes that I'm moving. They're magically teleporting back to the start just so I can kind of cycle through and continue moving them forward from one location to the next. Now on the right, we can see those probed results. So most importantly, you can see this torque one, the third one from the top. So for this ramp profile where I start from rest and I kind of move up to some given speed, I can see what are the torque requirements for my system. All right, and then there are kind of two ways you can go from here. Either you take these torque values and you can really just take the data as is and maybe you know what you want to do with it. Or one other way is you can actually go into a tool like ServoSoft. So here we actually have a connector with MapleSim to go to ServoSoft. So I'm just going to open it up and I click this load button. So all it's doing is it's linking this app to my model, bringing in all that information. And because I've used this specific ramp component, it's automatically going to know which values to pull in. So it knows that I need my position, my velocity, and my thrust. I can then change things about my simulation, so how long it's going to last, what time step I'm going to take. I can even choose the output units I want to be able to load into ServoSoft, and then I hit simulate. And what this is going to do is it's just going to run a simulation just as we did before. And once it's done doing that, it's actually going to give me some plots. So these plots help me to just look at the data before I actually export it, making sure it's exactly what I was expecting, or that I'm not seeing anything too crazy before I move to the next step. So if I'm happy with all of this, I scroll down, and then I can just choose a location and a name for this data, and then I just hit export. And right away, this is just going to give me a nice formatted Excel data sheet, and I can bring this into ServoSoft. So we're really taking all that effort out of having to hand calculate and punch in those numbers and figure out all those, steps that you were showing previously in ServoSoft. When you can just get them kind of for free or a lot easier, just makes things a bit nicer. right? So now we can, with this data, we can go into ServoSoft, kind of take all this information and use the import feature.
Mm-hmm. Yeah, so I can talk through this real quick. So I've opened up one of those sequences that we looked at before. There's an import option that you can see there. So if I click that, you'll see I have some different checkboxes here. So you want to make sure that this matches the data that you're going to import. So I've just checked the appropriate boxes. And then now I'm just going to open the Excel file that was generated from MapleSim, and you can verify all that data, scroll down and make sure everything looks good. And then once that data gets imported, again, we can see that we've got our, four different columns there, values. And once I hit OK, now we see that data plotted out as a sequence inside of ServoSoft. And from here, I've now got enough information to size my motor because I've got all the torques and speeds in the system. And I can move on to selecting my motor to make sure that I'm meeting, the required values that were exported from MapleSim, and making sure that the rated values of the motor are matching those or exceeding those for the system. So I think
so it really just goes to show how a tool can really just kind of simplify some of these processes, or allow you to design something a bit more complicated and really get you to that next step of just figuring out which motor and which drive do I actually need.
Yep, exactly. And the one last thing I wanted to get a look at is, I know there's some capabilities within MapleSim to make kind of iterating across these different possible permutations of all the variables. So can you show us what that looks like?
Yeah, sure. So like you said, maybe you already have a motor, maybe you just want to try different scenarios. So here I'm going to have a parameter for my CPM, and I'm also going to have a parameter for the mass of those boxes. So these will be the two parameters I play with. Of course, you could have a lot more that maybe you're interested in. And we're going to go to another built-in app in MapleSim under our model analysis, and it's parameter sweep. So once this loads up, it grabs all the available parameters. I can then choose the ones I'm interested in. So again, CPM and the box mass, define my ranges, define the number of data points. I can then select what outputs I'm interested in. So of course, here I'm going to be looking at that motor torque, which is the focus today. I'm going to be interested in the maximum absolute value. So normally I would just hit the button, but just in the interest of time, I've already got some results saved up. So we see those time results. And then we can choose the maximum absolute value, and then we can choose our two parameters, and we get this nice looking 3D graph. So with just a few clicks and without too much effort, I can really get this nice insight into my model. I can see how changes in the CPM affect that maximum torque, how changes in the box mass affect that maximum torque. So, in these more complicated systems, this might be very useful just to be able to get more of an insight of what's going on, kind of figure out what's happening. Maybe it's not as simple as just I have, just a motor moving a very simple math, and it's a one-liner calculation. So again, this is kind of where having some tools that have not just simulation abilities, but these more detailed analyses kind of built in, and things that can just make it a bit easier to understand, really bring a lot of value. And I guess just kind of some of the other benefits of the simulation tool. So just to kind of recap, so MapleSim is an equation-based system-level modeling tool. This means that as you bring in all those components into your model, what it's doing is it's just looking at those fundamental equations. We don't do anything fancy other than if you want this type of equation or this type of component, we bring in those equations and we connect them and we just solve those. It is also multi-domain. So in this example, it was a lot more mechanical, but if you wanted to add maybe an electric motor, you would be able to incorporate an electric motor into your model. And even it can be multi-domain. So it doesn't have to be just two, it could be 3, 4, hydraulics, thermal, whatever you might want. Again, built-in apps. So we saw a couple today, those B&R connector apps, the ones that generate the ServoSoft data. There is also one that will generate an FMU for Automation Studio, model analysis, component generation, exporting. So again, FMU, so whether it's Automation Studio or just something more general, so to go to any software, can also just generate the C code for your model, which can then allows you to kind of bring it anywhere. And the big one for us is really flexibility. So that flexibility to really do whatever you really want to do in the software. Whether it's create your own component, you can actually bring the equations in, kind of set it up however you want. So if there's maybe something very specific in your application, or you have some very specific physics you want to model, we have that flexibility, and also the flexibility to create your own apps. So the ones that we saw today were built in, so they're not user defined. But using Maple and Maple's programming language, you can actually develop your own app to create your own analyses, which I think is a very strong feature of some of these simulation tools. So I think this kind of shows the good overview of what you can do with a simulation tool for motor sizing specifically, and just some of the benefits of having these softwares.
Yeah, I think simulation-based approaches are going to be more and more common as we look at more complicated mechanics and looking at squeezing the most performance and efficiency out of our systems as we can. So I think we looked at how we can export to ServoSoft today, but there's a lot of other applications for simulation, right? You mentioned a couple of them. Potentially exporting FMUs or C code to actually execute at runtime on your PLC. There's some really interesting applications there. So yeah, this was a really good introduction to MapleSim and just simulation in general, how you can use that to enhance your motor sizing one step further. What's kind of your biggest takeaway, or the biggest thing you want the viewers to take away from this discussion?
Yeah, I mean, I guess if one takeaway would just be that if you're using a system level modeling tool such as MapleSim, you can really easily test concepts in these what if scenarios. So, if you change a parameter, if you add a load or change a load, what's going to be the effect on forces and torques in the system? And I think this just really gives you a deeper understanding of what's going on, which is, always beneficial.
Mm-hmm. Excellent. Well, thank you for joining us, Blake. I really appreciate it.
Thank you so much, Corey.
All right, so that wraps up our episode on motor sizing. To give us a quick recap, we looked at 3 approaches to motor sizing, and hopefully you have the information to understand which one is best for you. So the first of those was kind of the manual approach, where we're looking at crunching the numbers by hand or in Excel. From there, kind of the next level would be a software-based approach using a tool like ServoSoft. The advantage there is all of the equations and mechanics are pre-built, the transformations are pre-built, as well as a direct connection to a database of vendor products like a B&R servo motor, drive, gearboxes. You can pull all of the system dynamics in from that directly, so you don't have to go into the data sheet, pull the values, and crunch it in Excel. It's all there for you. And then the kind of last step, maybe the highest level of resolution, would be looking at a simulation-based approach to motor sizing with a tool like MapleSim. So we mentioned with MapleSim, you can build out your system using your CAD models. You can define all of the joints, the transformations, and then from there run the simulation and get that output file that you can then bring into ServoSoft, so you can still take advantage of that nice database of motors and drives to finish out the sizing effort. But depending on the complexity of your application and how important the efficiency of the system is for you, any one of those could be a viable approach. Certainly the simulation base is going to squeeze the most performance out of your system, and the manual one is going to be maybe the most effort, but there are certainly use cases for all of them. But again, the important thing I think to remember is that the workflow is pretty much the same regardless which approach you're using. Again, you're going to define the electrical characteristics, the mechanics, your loads and torques, select your motor, and then iterate from there. And it is an iterative process. Sometimes takes longer than you would like, but ultimately it will help you make sure you have the right size motor in your system, performing at the highest performance levels and the best efficiencies. So thank you for joining this episode of This is Automation. If you haven't already, I'd like you to subscribe to the channel and set up a notification so you can make sure you get all of the latest episodes and you get a notification every time we go live so you can join us. If you have any questions or comments, please leave those below and we'll make sure we get back to those. I do read all of the comments. And if you've liked, shared, or commented on anything, I just wanted to say thank you. It does mean a lot, and we appreciate it. So that is it for today, and we will see you next time on This is Automation.